Okay. So at the top it says learning goals, students will apply the product rule for differentiation. And the first thing I list is the product rule. So let's say you're trying to take the derivative, let's say you're trying to take the derivative of an expression where you have two functions being multiplied together, right? In this case, they're calling it function f and function g. Okay. What the product rule says to do is first find the derivative of f and just multiply it by g, just as it is. Not the derivative of g, just whatever the function g is. Plus, then you leave f alone. It just wants to know what the original function f looks like. Not the derivative, just the original function, times g prime, which is the derivative of g. Okay? So it's the derivative of the first times the second, plus the first times the derivative of the second. Okay? So that's the way I like to think about it. The derivative of a product of factors is equal to the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. We're just going to keep saying it over and over again. One thing I want you to keep in mind is that the derivative of f times g is not equal to the derivative of f times the derivative of g. So let's just take an example here. Let's do x times x squared plus 1. Okay, let's think about that. Currently, if I wanted to take the derivative of it without the product rule, I'd have to distribute this through, and we would get x cubed plus x. Right? This is my original function f. We'll call it f. Okay. So what would be f prime? That would be 3x squared plus 1. Right? That's what the derivative is. Please note that if I just take the derivative of the first expression times the derivative of the second expression, that is not what the derivative actually is. Does everyone see that? Okay, so don't make that mistake. Okay, you cannot do this. You have to use the product rule if you're taking the derivative of f times g. Okay? Or, if you don't want to use the product rule, you could do what we did here, where you multiply it all out to get it in standard form first, and then take the derivative. Okay, so you're either multiplying it all out and taking the derivative, or you're using the product rule. Yeah.
So when we're taking
I will not, but there are some problems where you will have to use the product rule, which we'll see here in a second. Okay, so for all of these problems that follow, it says find the derivative. If a c value is given, find the slope of the tangent line at x equals c. All right, so here's my first example. So, Danielle, going back to what you said, here's your first option, where you don't necessarily have to use the product rule. You could just multiply these and get that your function m of x is equal to 6x to the fifth, right? That's just doing a rewrite. I haven't taken the derivative yet. I'm just multiplying that expression out. Okay? Once it's multiplied out, then I can take the derivative. Notice how my notation changes to m prime, and that would be 30x to the fourth. Option 1. Option 2. Is to use the product rule. Again, for the product rule, what we do is we take the derivative of the first times the second plus the first times the derivative of the second. Okay, that's my product rule. I'm thinking about 3x squared like it's my function f. And I'm thinking about 2x cubed like it's my function g. Okay? That's the idea. I just labeled this. Here, I'll rewrite it down here. I'm thinking of 3x squared like it's my function f. And I'm thinking of 2x cubed, like it's my function g. Like we have two functions that are being multiplied together, okay, and I want to take the derivative of that. And here's what I do. I take the derivative of the first. What would be the derivative of 3x squared? 6x. Okay. Times the second. Okay, I'm just multiplying it by whatever g is. I'm not changing g at all. Plus the first function, just regular, not multiplied out or anything, or not taking the derivative of or anything, just the regular 3x squared function, times g prime, the derivative of the second. What's the derivative of the second? 2x cubed. 6x squared. Any questions about how I got to that point? In my head, I always say the derivative of the first times the second plus the first times the derivative of the second. I can say that over and over again in my mind when I'm doing this problem. Okay, so now I can simplify this. This is m prime. If I simplify this, we would get 6 times 2, which is 12. X to the, if I add exponents here, I get x to the 4th, plus 6 times 3 is 18. X to the, again, if I add the exponents, I get x to the 4th. Okay. 8, 9, 10, carry the 1, we would get 30x to the 4th. So see how we still end up with the same answer for the derivative, it's just a different method. Any questions about that? I'm going to get away from writing this every single time, so I'll just keep saying it instead. The derivative of the first times the second plus the first times the derivative of the second. Okay. So for example 2, we have m of x equals x squared times sine x. I want you to notice that this is really two functions being multiplied together. See how I have a variable here and then sine x here? That is different than what we've done in the past. In the past, we've done things like 5 sine x. See how there was not a variable out front before? It was just a constant. Two different things. If it's just a constant out front, just take the derivative of k sine x. The derivative of this would be 5 cosine x, right? But if you have a variable out front, this is the product rule. This one you have to use the product rule on. X squared is not a constant, okay? So I would make a note here, you must use product rule. Because if you notice, this, what we did in the past, was a constant. Or here, this is a variable out front. Okay, you actually have two functions being multiplied together. Does that make sense? Common mistake. So I'm going to think about this like it's my function f, and I'm going to think about this guy like it's my function g. M prime. We're going to take the derivative of the first. Derivative, let's just go around the room. Okay, I'll start with you. Derivative of x squared is 2x. Times the second, just regular. Conrad, what would you put? The derivative of the first times the second. You're good. Sine x. Right? This is the derivative of the first times the second plus. Now we're just doing the first regular, so what would I put that? X squared times the derivative of the second. So what would you put for the
Cosine x.
Good. The derivative of sine x is cosine x. Okay. Any questions about how I set that up? So really, that's all I can do. Right? I really don't need all the parentheses. I can drop most of them. 2x sine x plus x squared cosine x. I really didn't do anything but drop the parentheses that were unnecessary. Any questions about that? Example 3, this is another example where really you have two options. You could first rewrite this as x to the 1/2 times x squared plus 4 and multiply it through, right? Use the distributive property to multiply it out and then take the derivative. Okay, but today I really want to focus on the product rule, so I'm going to use the product rule with this. Let's go ahead. And we're going to look at x to the 1/2 like it's our function f. And I'm going to look at x squared plus 4 like it's my function g. So m prime of x equals derivative of the first. Now help me find the derivative of x to the 1/2.
1/2 x negative 1/2.
Great. When I subtract 1 from 1/2 in the exponent, you will get negative 1/2. Good. That's the derivative of the first, right? Times the second. So Bryce, what would I put there? Good. X squared plus 4. This is how it already is. Plus the first. So Maddie, what would I put there? Yep, square root of x, or I'm just going to leave it as x to the 1/2. Times the derivative of the second. So Mallory, what would I put there? 2x. Okay. Any questions about that? Now this looks kind of crazy. I'm going to clean it up a little bit so that I don't have negative exponents and I don't have fractional exponents. Okay. So I'm going to have m prime of x equals, this would really be 1/2 times, what would that be? Really, the x would move down to the denominator, right? And rather than writing x to the 1/2 in the denominator, I'm just going to write the square root of x in the denominator. Is that okay? Times the second, x squared plus 4, plus, over here, we would have the square root of x times 2x. Okay? Again, I'm going to try to clean this up just a little bit more. I'm going to put the x squared plus 4 up top. So we have x squared plus 4 over 2 times the square root of x plus, I'm going to call this 2x radical x. Everyone okay with that? And let's talk about how you would get it over a common denominator. If I want to have a common denominator of 2 radical x, if I put a 2 radical x down here, what else do I have to do? What do you think? What would you do? Yeah, I got to multiply the numerator by the same thing. So it's really like I'm multiplying the expression by 1, right? Anything divided by itself is 1. I'm just multiplying by 1, but it'll help me rewrite it over a common denominator. So we'll have m prime, the derivative, is equivalent to x squared plus 4. And I'm just going to write the whole thing over 2 radical x now. What would this be? 2 times 2 is 4, right? We have 4x times, what is the square root of x times the square root of x? It's x. So really this term right here, rather than writing 4x times x, really this is 4x squared. Does everyone agree? Okay, so I can combine 4x squared with the other x squared here. Prime of x equals, this would become 5x squared plus 4 over 2 radical x, 2 times the square root of x. Any questions about that? That one took a lot of cleanup. What we got there. You okay? Can we move on to the next one? Alright, in example 4, we have our function x sine x. Again, notice that this is really two functions being multiplied together. X is our first function, sine x is our second function. And different than having a constant out front of sin x. Okay, in this example, you have to use the product rule. And you might make a note that you must use product rule. For this example. Okay? There's no way to get around it. You have to use it. So I'm going to find my f prime. Did I leave off? 4. Then you get to your f, girl. Derivative of the first? 1. Great. And then times the second, Danielle? Just sin x. Yep. Derivative of the first is times the second regular plus the first regular x. Yep. Times the derivative of the second. So what would the derivative of sin x be? Cosine x. Okay. Again, keep in mind this is the derivative of the first times the second plus the first times the derivative of the second. So at this point, we can clean this up a little bit. We would just have sin x plus x cosine x. Agree? Now let's say that I want to find the slope of the tangent line at the c value pi over 3. What do I do with the pi over 3? Plug it in for x. So I have f prime of pi over 3 equals sine of pi over 3 plus pi over 3 times the cosine of pi over 3. Remember, pi over 3 is the 60-degree reference angle. Across from 60 is radical 3. Across from 30 is 1. Hypotenuse is 2. Okay, everything's positive in the first quadrant. Okay. Jordan, what would be the sine of pi over 3? Great, radical 3 over 2. Right. Sine is opposite over hypotenuse. Plus pi over 3 times the cosine of pi over 3. What would you get for cosine of pi over 3? Connor, coming over to you.
60 degrees.
Pi over 3 is 60 degrees. Yes, what's the cosine of pi over 3?
Oh, 1/2.
1/2. Any questions there? Okay, so now we just need to rewrite our final answer. Okay, so we have radical 3 over 2 plus, here top times top is pi, and bottom times bottom is 6. Okay, so I somehow need to get a common denominator here. What is this denominator missing that that denominator has? A 3, right? 6 is 2 times 3, so this denominator is missing a 3. So whatever I do to the bottom, I'm going to do to the top as well. This will be equal to 3 radical 3 plus pi over 6. Any questions about that? Anything at all? Okay. Now, one comment I do want to make, I'm going to stop there for now. One comment I do want to make is don't forget that you can check this using your graphing calculator, right? Remember in your graphing calculator, you could go to Math 8 to check your derivative. Okay? Or if you like this method better, you could go to y equals, type in your function, do second calculate, dy dx, and then type in whatever constant you're trying to evaluate. Okay? So there's 2 different methods. I'm going to go over both of them with you. We're just going to go through and check some of our answers. Okay, so I'm going to pop back to, where's the first one we see? This is really the only one where we plugged in a C value, right? So let's go ahead and check that. First of all, I'm going to figure out what 3 radical 3 plus pi divided by 6 is approximately, right? Because our decimal approximation is going to be important for checking our work. Okay, so I'll do 3 times the square root of 3 plus pi, press enter, divided by 6. Okay, so I get about 1.38 or 1.39, right? I guess if you round it up, it would be 1.39. So keep that in mind. Okay, that's what answer we got. Now what I'm going to do on my calculator to check my work is I know that my function is x sine x. I'm going to go to math, arrow down to number 8. Okay, and I'm differentiating with respect to x. Zoom in here. I'm differentiating with respect to x. I'm going to put in my function, which is x sine x. Okay. Close my parenthesis. Okay, and then what x value am I trying to plug in? Pi over 3. Okay. If you have an older calculator, remember that you're going to put the function first. So it would be x sine x, comma, x, comma, pi over 3. So it's a little bit different order. Press enter. See how we still get 1.39? Pretty cool. The calculator is just approximating that final value. So sometimes what you get on your calculator might be a little bit different than what you get for your answer, right? Like maybe like 0.01 of a difference, which rounding wise, that does make a difference. Okay. Another way you could do it is go to your y equals and type in your function here, x sine x. Okay. And you can go into your second calculate. See how there's dy dx? Might have to wait a second. And I did not do a zoom trig, so ignore my graph. Okay, after I do a second calculate dy dx, I'm just typing in pi over 3. Second pi over 3. Okay, and what you want to pay attention to is this part right here. Dy dx equals 1.39. Any questions for me? What I want you to do right now is I want you to work through number 1 through 9 on the worksheet that you picked up on your way in.